Anyone familiar with bicycles knows that a bike's derailleur is actuated by a cable. This steel cable is the bike's gear shift cable. Looks can be deceiving. Don't be fooled by its mere 1.2mm diameter. We tested its strength on a Tensile machine and it's around 1,500 newtons. It could lift 2 people my size without breaking a sweat. But sharp-eyed viewers might have noticed that 2 shackles above and below the cable. You might not believe it, but those shackles are 3D printed. The steel cable snapped, but the printed parts only suffered superficial scratches. Of course, this isn't ordinary FDM printing. It is a technique called continuous fiber reinforced 3D printing. You might not have heard of it because machines that print with continuous carbon fiber used to be prohibitively expensive. Now, Fiberseek has brought this technology down to under $3,000 with the Fiberseek 3. In terms of strength, it absolutely outperforms standard FDM and resin printing. So, what exactly is this continuous fiber printing technology and how we can use it? Let's explore together in this video. Carbon fiber is an incredibly high-performance material. Its tensile strength is twice that of aerospace-grade aluminum alloy, and while its stiffness is comparable to steel, it weighs a fraction of the weight at less than a quarter the density. However, continuous carbon fiber is incredibly stiff and doesn't melt, making it incompatible with standard FDM setups. So, engineers came up with a workaround: chop the fibers into tiny particles and mix them into plastic. This at least enhances the plastic's strength and stiffness somewhat. That's how we got the carbon fiber filament you commonly see today, technically known as short carbon fiber reinforced filament. But here's the catch: a carbon fiber strength is highest along its length. Without continuous filaments bearing the load, it's like fighting with one arm tied behind your back. Short fiber reinforcement is essentially a compromise for the sake of easier processing. So, is there a way to embed continuous long fiber strands into a printed part to act as reinforcement? Yes, but the challenges are huge. Unlike traditional FDM, where plastic melts and flows easily, carbon fiber strands are rigid. Feeding a single continuous strand through a tiny nozzle is already a technical feat. Worse yet, if the material doesn't cool sufficiently, the moving print head can actually tear apart the already printed sections before they have a chance to set. Fiberseek is backed by the heritage of Anisoprint, a company with years of experience in commercial-grade continuous fiber printing. Their goal was to bring this technology down to the consumer level, giving birth to the Fiberseek 3. At first glance, or even under the hood, the Fiberseek 3 might look like a standard FDM printer. It features a Core SY structure, a build volume of 300 by 300 by 245 mm, a 350°C nozzle, a 110°C heat bed, and a 65°C heat chamber. It also supports AI camera monitoring, automatic leveling, filament runout detection, clock detection, and pressure advance. But here's where things get interesting. It uses a dual extruder setup. The right side is a traditional FDM hot end. This part is identical to a standard FDM and can handle various materials like PLA, PTG, ABS, nylon, and more. The left side's hot end is the continuous fiber reinforcement print head. This head has 2 filament inlets, one for the continuous fiber strand and another for the traditional FDM plastic filament. Inside the chamber, the plastic melts and encapsulates the carbon fiber as it's extruded. Fiberseek call this their continuous fiber co-extrusion technology. So, how strong is this technology? I'm sure you want some hard data. We performed a standard tensile test according to ASTM T3039. For the control group, we use a Bamboo Lab H2D with PPACF, the strongest consumer-grade short fiber material, to print a specimen 50mm wide and 1mm thick. On the Fiberseek 3 side, we printed the same specimen in pure fiber mode, using just a small amount of PTG as the binder. First, guess how much force the PPACF sample could withstand? The answer is just over 2,000 newtons. It's hard to believe an FDM printed strip like this could lift over 200 kilograms. This makes us even more curious. Just how insane would this continual fiber printed sample be? The maximum force exceeded 17 kilonewtons. To put that into perspective, this tiny strip could theoretically lift a Tesla Model 3. During our experiments, we even tried to snap the shackle from the start of the video. However, the test rig's hook failed at 3 kilonewtons before the part would break. Looks like I still underestimated the power of continuous carbon fiber. So in terms of strength, continuous fiber printing unquestionably crushes traditional FDM. We also observed during the tensile test that continuous carbon fiber stiffness is far superior to short fiber companies. This led us to another question. In the cantilever bending scenario, can adding a small amount of carbon fiber improve bending stiffness? So we printed a cantilever hook with 1, 2, and 4 rings of carbon fiber inside to see the effect on rigidity. As you can see, compared to a structure without fiber reinforcements, just 1 ring of carbon fiber significantly reduces deformation. This might be the most cost-effective way to add fiber reinforcements, and printing more rings gives you even higher structural stiffness. After addressing performance questions, your next one might be, is a continuous fiber printer difficult to use? Actually, the Fiberseek 3's UI is quite user-friendly. It's just 1 extra fiber spool compared to FDM. We believe anyone can get a hang of it quickly. This machine has 3 independent printing modes using a color coding system inspired by industrial indicator lights. Green light indicates pure matrix mode. Here, also known as high-speed mode, it acts as a standard FDM machine for printing pure plastics or short fiber filaments. Orange light indicates the most commonly used high-strength mode. Here, plastic coats the outside of the fiber, much like the shackle from the intro, looking harmless but packing a serious punch. The tensile test samples came from purple light mode, also called pure fiber mode. Without a plastic layer covering it, the part surface is rougher, but the performance of continuous fiber printing is fully unleashed. This is useful for critical load-bearing structures in fields like aerospace or high-performance racing. A nice detail is the colored light also acts as a progress bar, so even from a distance, you can easily see the print's progress and status. On the software side, continuous fiber printing logic is completely different from traditional FDM. It requires placing the strongest material exactly where the loads are highest. This is indeed one of the core technologies, and IsoPrint provides their self-developed software, Rocket Slicer. Unlike the open-source FDM slicers we're used to, Rocket Slicer not only handles FDM but also plans the continuous fiber parts. You can freely allocate where and how much fiber to use, like reinforcing the shell or the infill. For different needs, Rocket Slicer offers various templates. You can adjust print modes, lattice infill patterns, and densities based on these templates. The software also auto-optimizes based on your model's geometry to maximize fiber performance. With so many advantages, you might wonder, is continuous fiber printing a universal, game-changing new tech? The truth is, it has limitations. In the 3-axis printing environment, continuous fibers are only distributed within the XY plane of the structure. That's why XY strength is exceptional, but Z-axis strength still relies mainly on the thermoplastic matrix. If you need strength in all directions, you would need a 5-axis continuous fiber printer. Another issue is that continuous fiber printing speed is currently relatively slow. The Fiberseek 3's fiber printing speed is 20 milliliters per hour. This video is not slowed down. I wonder if you can accept the speed or not. To print ultra-high-strength continuous fiber materials, you have to work with the fiber's characteristics. Even industrial-grade machines face this. Speed is just a matter of time, but having the capability or not is a world of difference. The core appeal of the Fiberseek 3 lies in breaking the $3,000 barrier and bringing industrial continuous fiber printing to the consumer market. We can now easily 3D print high-strength parts, like this drone landing gear. Traditional FDM printed ones are prone to breaking in the crash, but continuous fiber printed ones hold up much better. The strength and stiffness can already replace some metal parts. This also includes printing ultra-strong hooks capable of lifting a car. Beyond the scenarios we've shown, we wonder what new applications you can imagine. We look forward to your ideas in the comments. Finally, you might be thinking, even if the machine is affordable, isn't the carbon fiber material still expensive? Will I be able to afford the machine but not the costly consumables? Fiberseek's solution is simple. A 500-meter spool of 1K continuous carbon fiber costs just $49. Compare that to competitors who sell similar material for around $300. If that's still too steep, you can opt for more affordable glass fiber materials. The price is much more accessible, and performance reaches about 50 to 60% of carbon fibers. I think this is quite affordable for everyday applications and 3D printing education in universities. So, we genuinely hope the Fiberseek 3 can bring everyone a brand new experience with continuous fiber-reinforced 3D printing. The Fiberseek 3 is currently live on Kickstarter. Those with internationally enabled credit card can enjoy super early bird benefits. Secure yours with a $50 deposit now to lock in the super low price of $23.99. The mass production version for the domestic market is expected to launch in March. Let's look forward to the answer of Fiberseek provides. Okay, that's all for this video. I'm Koala. Please give me a like, subscribe, and follow me for more cutting-edge tech in the 3D printing technology.